Hi guys, Miss O'Connell here. So we're going to be continuing our discussion on constant acceleration, the big four. Okay, so the equations are listed below. First equation, velocity equals initial velocity plus the acceleration times time. Okay, that equation comes from the velocity versus time graph. Okay, it's in the form y equals mx plus b. The y is actually the velocity. The y-intercept is the initial velocity. The slope of a velocity graph is the acceleration. And then the x value on a velocity versus time graph is time. Okay, so final velocity equals the initial velocity plus the acceleration times time. Okay, next equation, which we discussed a little bit yesterday, right? Change in displacement equals initial velocity times time plus 1/2 the acceleration times time squared. Final velocity squared equals initial velocity squared plus 2 times the acceleration times displacement, also known as the change in position measured in meters. Last equation we discussed and did a few examples of yesterday. Please pause the video and make sure you have all of these equations written on your note card under the title Constant Acceleration. Once you have those written, please open your packet to the next examples. Okay, so the title of those examples are called Finding Velocity. Okay, so example 1. A car enters the freeway with a speed of 6.4 meters per second and accelerates uniformly at 0.2 meters per second squared for 3.2 minutes. How fast is the car moving after this time? Okay, so we draw a little diagram. We know that the initial speed, V initial, is 6.4 meters per second. The acceleration rate is 0.2 meters per second squared. We're told that that's constant or uniform, so we know we have to use the big four. The time that it takes is 3.2 minutes. We should notice immediately, right, that those units do not match and that we need to convert minutes to seconds. So there are 60 seconds in 1 minute. So we're going to take 3.2 and multiply by 60. We get 192 seconds. Okay, so I'm looking for my final velocity. I know my initial, my acceleration rate, and my time. I'm not given delta x and I don't need it, so I'm going to use the first equation. V equals V naught plus a times t. I'm solving for velocity, so I'm going to leave that as a variable and plug in what I know. Initial velocity is 6.4 meters per second plus 0.2 meters per second times 192 seconds. When you plug that into your calculator, you're going to get 6.4 meters per second plus 0.2 times 192 seconds. Units there, we will have meters per second. The final velocity is 44.8 meters per second. You see that one of these seconds will cancel and we'll have meters per second plus meters per second. So our units are meters per second, which is exactly what we need. So the final velocity of this car will be 44.8 meters per second after 192 seconds have passed. Okay, so this car is speeding up and in the positive direction. Velocity and acceleration are both positive. Okay, so let's head to example number 2. Also finding velocity. This should look a little familiar to you, except in this same situation, we're looking for the final speed of the plane. So example 2, a plane starting at rest at one end of a runway undergoes a uniform acceleration of 4.8 meters per second per second for 15 seconds before takeoff. What is the speed at takeoff? Okay, so we can draw our nice little diagram of our plane on the runway. Okay, or in my situation, looks more like a shark on wheels. Okay, but draw your diagram. The initial velocity of the plane is 0. The constant or uniform acceleration is 4.8 meters per second squared, right? And those words, uniform acceleration, tell us that we can use the big 4 equations to solve for the final speed. When they say speed, right, they really mean velocity. So we're looking for that final velocity after 15 seconds have passed. So again, we're not given delta x, we don't need it. We're looking for final velocity and we're given initial acceleration and time. So we can use the first equation. You can use any combination of the 2 equations and you will get the correct answer, but we can use the first equation and do this problem in one step. So I'm looking for final velocity, so I'll leave that as a variable and plug in what I know. When we plug that into our calculator, we will get that the final velocity of our plane is 72 meters per second. So velocity at takeoff, 15 seconds from the beginning of the runway, will be 72 meters per second. Again, object speeds up because acceleration and final velocity are both positive. So it speeds up in the positive direction. Okay, so let's take a look at example 3, still under finding velocity. So in example 3, we have a car, an automobile, with an initial speed of 4.3 meters per second, accelerates uniformly at the rate of 3 meters per second squared. Find the final speed and displacement after 5 seconds. Okay, so again, we can draw our nice diagram. We know that our initial speed is 4.3 meters per second. Our constant acceleration rate is 3 meters per second squared. This occurs over a 5-second interval. We want to find our final speed and our displacement. So first, we're looking for final speed. We can use equation 1, as we have been in the previous 2 examples, to find that final speed. We plug in what we know and leave what we don't know as a variable. We get that the final velocity of our car is 19.3 meters per second. Okay, so speeding up in the positive direction. We need displacement. We can really use a number of equations. We can use a number of equations to find displacement. The easiest one to use would most likely be equation 4, because that equation is already manipulated to solve for delta x. But again, you can use any combination of equations as long as they contain the variable you're looking for. So there's no right or wrong equation to choose from here. But I'm going to choose equation number 4. So I'm going to take my final velocity plus the initial velocity divided by 2 times time. So I'll have 19.3 meters per second plus 4.3 meters per second divided by 2 times the time interval, which we're told is 5 seconds. So again, plug this into your calculator. Make sure you're doing order of operations correctly. You have 19.3 plus 4.3. Divide that by 2. You'll get 11.8 meters per second. 11.8 meters per second times 5. I get 59. So delta x is 59. Okay, so units, I had meters per second times seconds. The seconds cancel out. I'm left with just meters. Okay, so pretty remarkable, right? We're given 3 variables, but we are able to find 2 additional variables using the big 4. So we know the final speed of the car after 5 seconds, and we know how far it has traveled, which is 59 meters. Okay, so you can now give the rest of the practice problems a try. So from the worksheet in the back of the packet, constant acceleration examples, you can now try numbers 2 through 5 on the homework. Okay, please email me if you have any additional questions. Make sure that you took notes on these videos. I will be checking these notes as a classwork grade. Have a great day.